Okay, we continue the discussion on the Rodrigues formula in section 15.1. Last time we showed that the form of the Rodrigues formula is given by this. The n derivative of this factor 1 minus x squared to the power n. This factor is basically the p in the Legendre equation, 1 minus x squared. Okay, and we showed that the last time the conventional definition of the Legendre polynomial will involve a coefficient in front of that, but this time I want to show that this expression for yn satisfies the Legendre equation directly. This is not in your textbook, but I want to show that because in section 12.1 we already discussed the general formula for the Rodrigues formula that they satisfy the ODE, this one directly. But for the special case for the Rodrigues formula for Legendre polynomial, we can try to show that explicitly this satisfies this one. Okay, so the idea is that we'll just directly substitute this one into here and see what happened. Okay, so now we try to do 1 minus x squared yn double pi. Okay, so that's basically this term. Now this is equals to, we can write it explicitly, 1 minus x squared double pi is just second derivative, so it becomes d dx of n plus 2 power and operate on this factor 1 minus x squared to the power n. Okay, and what we want to do now is to use the Leibniz formula, and to do so we're doing something like a integration by parts. So we'll get one of the derivative out in front of the whole factor. So we'll write it like this is equals to actually we want to get the n plus 1 out of the factor, not just 1, d dx to the n plus 1 power out. So d dx to the n plus 1 factor out. So this is we'll have 1 minus x squared times d dx of this one. So d dx of 1 minus x squared to the power n. Okay, this is not all of them because this is n plus 1 derivative of this one using the Leibniz formula. So it will get the first term will be this one. So basically n plus 1 derivative operate on this one, give you n plus 2 derivative and multiply by the 0 derivative of this one, which is just 1 minus x squared. So that's the first term. And now you can need to subtract other terms. The next term would be the n derivative of this term times the first derivative of this term multiplied by the coefficient. The coefficient basically is like the coefficients of binomial expansion. So that one would be, so you need to subtract the first one in the n plus 1 binomial expansion is n plus 1. Okay, and now the first derivative of this one will give you minus 2x. Okay, and then the n derivative of this one will give you back the dx to the n plus 1 because your n derivative and then 1 derivative in here. Operate on minus x squared to the n power. Okay, so now that's the second term. and then the next one would be the second derivative of this one times the n minus derivative of this one at the times the n minus 1 derivative of this one, and multiply by the coefficient, of course, so you subtract another one. And the coefficient for that term is it's n plus 1 times, the next one is n, so n plus 1 times n divided by 2 factorial, which is just 2. Okay, and the second derivative of this one, which is the derivative of this one, and which is minus 2. And then the n minus 2 derivative of this one will give you back d dx n 1 minus x squared to the n power. Okay, so then supposedly you have higher order term, but then you have the third order term will involve the third derivative of this one, but the third derivative of this one and any higher derivative of this one will be 0 because this is just up to x squared. So this is all. So this one subtract this one, subtract this one. Okay, and now we can continue to simplify this one. Okay, and to do that we can work out the derivative of this one explicitly. So this one equals to d dx n plus 1 power. The derivative is quite straightforward, so it's n and times 1 minus x squared to the n minus 1 power, but you multiply by this one, 1 minus x squared, so you get back to n power 1 minus x squared to the n power. But then you need the derivative, take a derivative of minus x squared, so you give you minus 2x. Okay, so that work out the derivative of this one explicitly. Okay, then all these you can simplify those a little bit. So you have minus and minus is plus 2 n plus 1. Now you can use this expression to simplify this one, because this is 1 minus x squared to the power n, and then n plus 1 derivatives. So n derivative is yn, so this is the derivatives of yn, so this is yn prime. Okay, and for this one, you have also minus minus, and 2 cancel with 2, so you have plus n times n plus 1, and the rest is just yn. This one is just this one, so it's just yn. All right, and now we want to continue to simplify this one, and what we'll do is use the Leibniz formula again, and now you have x factor and then 1 minus x squared to the power n, and this coefficient you can pull those out, minus 2 times n, and then times the Leibniz formula. So the first term is take the n plus 1 derivative of this one times the 0 derivative of this one, which is just x. Okay, and then the n plus 1 derivative of this one, so d dx, the n plus 1 minus x squared to the power n. Okay, so this is this one. And the next one is the next term is the first derivative of that and times the n derivative of this one. Okay, and multiply by the coefficient, which is n plus 1, so it's plus n plus 1. The first derivative of x is just 1, and so you get and the n derivative of this one, so you get d dx of n 1 minus x squared to the power n. So this is this one. The rest is just plus 2 n plus 1 yn pi. Just copy the rest. Okay, now we can do the same thing to simplify this and that using this formula. So what you have is the first one is minus 2n x, and this one is just basically yn pi, okay, and this one I forgot the x. There's an x here. There's an x here. Okay. There's an x here. Okay, and then the next one is minus 2 times n plus 1. The n plus 1, and the rest is just yn. Okay. And then you have this plus 2 times n plus 1 x yn pi plus n times n plus 1 yn. Okay. Now you can see that this minus 2nx yn pi, you have 2nx yn pi, so this one cancel with this one, just the n. So what is left is 2x yn pi. Okay, and this one is 2 times of this one with the negative sign, so it's negative n times n plus 1 yn. So what is left is 2x yn pi minus n times n plus 1 yn. So this one equals to 2x yn pi minus n times n plus 1 yn. If you move these two terms to the left-hand side, you get 1 minus x squared yn double pi minus 2x yn pi plus n times n plus 1 yn equals to 0. So this shows that this is the solution. This is a solution, at least for the Legendre polynomial, Legendre equation with the eigenvalue n times n plus 1.